20 minutes.
For your kind introduction. And in the outset, I want to thanks organizer and for giving me the opportunity to talk in front of this. So my topic is chemical aspect of advanced nuclear reactor. If you see what are the generation of reactor still there, generation 1, generation 2, generation 3 and generation 4. From first generation 1 and generation 2 and generation 3, these reactors are derived from the nuclear propulsion with additional safety and security. Then in 2001, generation 4 International Forum was established. In this generation international forum, generation 4 reactors were introduced with the aim of improvement in thermal efficiency, enhancement of safety features, proliferation resistance enhancement, and advanced waste management with more economical and cost effective. In this generation 4 reactor system, 6 reactors were chosen, and among these, molten salt reactor is one of the non-classical liquid fuel reactor. Other 5 reactors are solid fuel reactor. So my talk will be on molten salt reactor because of time constraint. If you look into the history of molten salt reactor, the concept of molten salt reactor was given by Warren Lab in late 40s. In 1954, they have carried out this air-capped reactor experiment to validate that molten salt concept with this sodium, zirconium, uranium fluorides mixture. From 1965 to 69, molten salt reactor experiment was operated to know the viability of the scientific and technological issue related to the molten salt reactor. Then 1971 to 76, they go one step further, whether molten salt can be used as a beta reactor or not. So they have operated this reactor from 1971 to 76 with thorium as a blanket material for breeding, and with a breeding ratio of 1.06, they were achieved. After 1976, the project has stopped, and recently with the name of Gen 4 reactor system, this molten salt reactor has been given on priority to breeding as well as power production with more inherent safety features. So if you can see that mixture of fluoride salt are chosen most of the cases, almost all cases by the Warren Lab for molten salt reactor. So question is, why fluorides is more important as compared to other? If you can see the isotope of different non-metallic isotopes and their thermal neutron absorption cross-section between fluorine and chlorine, fluorine has a 2 isotopes, one is fluorine 35 and another is fluorine 37, but fluorine has one naturally occurring isotopes. So fluorine has less thermal neutron absorption cross-section as compared to chlorine, and it is less sensitive towards N-gamma reaction. And also other advantage is it has a low vapor pressure, high thermal stability, high thermal conductivity, and it is less non-stoichiometric compound as reported. In case of fluorine 35, because of its high neutron absorption cross-section, it cannot be used in thermal neutron reactor. Because thermal neutron reactor 35 fluorine, which is 75% in naturally occurring isotope, it undergoes N-gamma reaction to 36 fluorine, and it has a long half-life. So it can it should be enriched with 37 fluorine, which has a very less neutron absorption cross-section. For fast beta reactor, fluorine can be option, and their studies is going on in the recent year. Other non-metallic part, oxygen, nitrogen, sulfate, phosphates, oxides, carbonates, nitrates, sulfate and phosphate they can form. In terms of Newton absorption of cross-section, they are reasonable choice. But in case of chemical context, in the chemical context, they cannot be used because they have a high melting point. Sometimes they undergo thermal decomposition. They have a less radiation stability, and most of the cases they are not suitable for container material. They actually interact with the container material, so they are more corrosive. At the same time, one key features is that sometimes they cannot dissolve enough fissile or brittle material. Because enough fissile material dissolution is required in case of molten salt to reactor to be critical. So how to choose the salt? I have given these schematics of molten salt reactor where one is primary fuel salt which will be circulated inside the core, and another is outside the core. This is called secondary coolant salt. So this will be only cooling purpose, and this is fuel as well as primary coolant. In case of primary coolant, there is a two constant. One is nuclear constant and another is chemical constant. So nuclear constant is because it is inside core, so low thermal neutron cross section should be there for better economy of the neutron inside the reactor. At the same time, what are the different chemical constants? It should have a low melting point, low vapor pressure, high thermal conductivity, high heat capacity, high radiation stability, as well as it should not react with the structural material. But another key factor, as I said, solubility of the fissile material is very, very important and should be enough to make the reactor critical. So, in case of secondary coolant salt, there, because it is outside the core, there is no neutron economy or such thing is present, so no formal neutronic requirement is there. There should not be any enrichment requirement, and minimum solubility of fissile or fission product also not there. So our aim is to find out the salt mixture which have a melting point near about 500 degrees centigrade temperature, and it should not contain any beryllium fluoride or zirconium fluoride. As I said, in the ORNL they have used mostly beryllium fluoride, zirconium fluoride in their salt because beryllium is toxic, it has a high viscosity. At the same time, zirconium fluoride is also more volatile, so that should be redundant. Why 500 degrees centigrade temperature? Because mostly from our past experiment, it has been seen that molten salt reactor inlet temperature is 600 and outlet temperature is 700 degrees centigrade. So, as a safety margin, our melting point should be less than the inlet temperature, 100 degrees less than the inlet temperature. So, around 500 or 550 degrees centigrade temperature, we have to choose a salt mixture whose melting point is around that. So with this aim, Indian molten salt beta reactor has been established or given these schematics, and to utilize our domestic thorium efficiently in our nuclear program. So this is well known, everybody is known for thorium-uranium cycle, where thorium-232 undergo N-gamma reaction followed by 2 beta decay to give uranium-233 with a intermediate protactinium-233. So we have to separate this protactinium. I will come to later this protactinium separation. And selected fuel salt is lithium fluoride, calcium fluoride, thorium fluoride, and uranium. Because it is a beta reactor, thorium fluoride is one of the component. We have add calcium fluoride, although it has a melting point, higher melting point, because to minimize the content of lithium fluoride. Lithium undergo N-gamma reaction to give tritium, which is radiological hazardous. So we have to minimize content of the lithium fluoride, adding some calcium fluoride, but we cannot add so much because then melting point will be higher. At the same time, coolant salt is lithium fluoride, sodium fluoride, and potassium fluoride. So, as a chemist, our role is to prepare the salt. Before preparation, impurities has a great effect in molten salt reactor system and molten salt component. So what are the impurity basically contribute the chemical corrosion process, and they sometimes form solids which deposit in the primary circuit. So it is detrimental for the molten salt reactor. What are the different impurities present in the molten salt? Mainly oxide, moisture, and sulfur. Moisture, basically, most of the fluoride salts are hygroscopic in nature, so they form oxyfluoride or oxide. They have a low solubility, and sometimes they deposit in the solid as a solid particle in the reactor loop, so that should not be there. And so by anhydrous HF and hydrogen sparging in the molten salt, we can remove the moisture. What are the oxide sources? Because impurity water present in the raw material of the molten fluoride salts, fluoride salts, and also incomplete evaporation of the absorbed water during initial melting. That time also in situ oxide generation may be there, and that is the source of oxide impurity. They also form oxyfluorides of thorium or uranium. They have a low solubility and they deposit as a reactor loop as a solid particle. So they can be purified by HF or H2O purging. Sometimes we avoid to corrosive HF, we want to avoid that one, so we use ammonium bifluoride for safety and convenience. Another is sulfur. Sulfur is coming from when we are dissolving the ore into the concentrated nitric acid solution for extraction of the metal such as lithium, sodium. So that time this sulfur is coming, and this is a very corrosive towards the structural material like nickel based alloy. So we have to remove this using anhydrous HF(H2) sparging in the molten salt. This is the thermodynamic database we have produced in our lab. EMF cell, using EMF cell, differential scanning calorimeter, high temperature calorimeter. So now when under uranium 235, uranium 233 undergo fission, lot of fission product is produced, as you know. So I have categorized different fission products. Some fission products are always soluble in the molten salt, some are insoluble, some are partially soluble in the molten salt depending upon the redox potential inside the molten salt reactor. And obviously gaseous fission product is also generated, some krypton, xenon and radon. So, but however, short-lived fission product, that is very great concern due to their chemical and physical properties difference between the parent and daughter element. See, 99 zirconium, which is soluble, it is a fission product. After decay, it is going to 99 niobium, which is partially insoluble. Then within 15 seconds, it is undergo decay to 99 molybdenum and also 99 technetium. So this is the insoluble fission product. So there is a physical state is changing with decaying of this fission product. Because if you see this is the reactor core where typical residence time is less than 30 seconds. At the primary loop, the residence time of this molten salt is less than 30 seconds. So less than 30 seconds half-life nuclides are considered to be as a short-lived fission product in molten salt reactor, and they should be they should give some detrimental effect because of their physical and chemical properties changes. Another is one of the iodine 137, which is soluble, going to within 25 second decay half-life, 137 which is gaseous, and similarly 137 cesium is after 4 minutes and it is soluble. So because very short half-life of this fission product, experimental determination of their chemistry is very difficult. So we have to have some computational methods for provide some insight into the impact of the short-lived isotopes of the reactor chemistry and corrosion. So advanced computational methods should be there to study this type of short-lived fission products. Another fission product is tellurium, which has a very high vapor pressure. It's got intergranular cracking in the alloy through the gain boundary by this reaction. Uranium trifluoride plus chromium fluoride, which is present inside the reactor, I'll tell how. And then tellurium, it is going to chromium tellurides, and these chromium tellurides basically cause the intergranular cracking. So after fission product, what is the compatibility of the material, chemical compatibility, and what is the challenges? Because success of molten salt reactor is strongly dependent upon that. I have to contain the molten salt, otherwise we cannot operate a reactor. So there is different environment which is very actually hostile environment, radiation, fluorides and corrosion, high temperature. So the rate of corrosion depends upon the thermal gradient, galvanic coupling, redox species, flow rate, so many. So What are the different materials? Actually, studies, mostly nickel-based alloy has been studied in the molten salt reactor operation, because nickel is supposed to be one of the corrosion-resistant material. So what different corrosion reaction and how chromium is removed from the, because chromium is one of the alloying element in this nickel-based alloy. So how chromium is removed or reaction with chromium to the molten salt. One thing is that impurities. As I said, impurity has a very great effect. So this hydrogen fluoride, which is formed from the H2 or oxygen with metal, so that will give the chromium trifluorides. So it is remove the chromium by chromium fluoride and it is dissolved in the molten salt. Another is metallic impurities, which is already present in the molten in the fluoride salt, that can also react with the chromium to remove the chromium using this reaction. Another is very important, that is uranium tetrafluorides, which is one of the component salt for the fuel, and that is react with chromium to chromium fluorides and uranium trifluoride. So this reaction is always there. Without this reaction, uranium trifluoride, we cannot operate the reaction. So persistent corrosion is driven by this uranium trifluoride, uranium fluoride ratio. So we have to maintain the redox potential so that this reaction can be suppressed. Another is temperature gradient mass transfer corrosion, which is happen due to the solubility difference in higher temperature and lower temperature. So at higher temperature, chromium will be more soluble. When it is going to the lower part of the lower temperature, it will deposit it. So that is called temperature gradient mass transfer corrosion. So removal of this chromium, it will lead to the formation of voids and embrittlement in the alloy, and so the integrity of the alloy is lost. Another very interesting is lithium generation.
2 minutes.
Yes, sir. So lithium generation and its effect. Lithium fluoride, tritium generation. Lithium fluoride is N-alpha reaction to tritium fluoride. Tritium fluoride react with the chromium, give to the tritium gas. It has a very low solubility and it is radiological hazardous because diffuse out through the structural material very easily. So we have to have some redox control agent which can avoid this corrosion and the tritium gas production. So this is the one of the protactinium separation. As protactinium has a neutron absorption construction, so online separation of protactinium should be there for better neutron economy and high breeding ratio. So protactinium separation, in the literature I have seen that there is the 3 methods still that is present. One is oxide precipitation, where oxide protactinium is from the oxide by passing from thorium oxide into the salt, and it is react with the lithium to some protactinium pentafluoride lithium fluoride adder, and this is a solid particle that can be filtered out and separate from the liquid. It is very old, but there is a very cumbersome in oxide precipitation. Then it has to be converted to the fluoride and metal, and then have to take the protactinium. So in case of fluoride volatility method, where fluorine gas is passed through the protactinium tetrafluoride which is present in the salt to make the plutonium pentafluorides, that pentafluorides has a high volatility and that should be evaporated and collected, so we can separate like this way. Another is very well known is reductive extraction method using liquid bismuth. That this protactinium tetrafluoride that should reduce with some sodium metal as a reductant and then co-extracted with the liquid bismuth. That separation chemists, they are very well known to these things. So this is the status of the database in molten salt reactor as an overview. In this table, fuel carrier salts and fission products, structural material component and their mixture, how we have studied. This green block basically experimental thermodynamic data in the literature, and this violet is estimated thermodynamic data in the literature. This blue basically actually work carried out in PDD, FCD and RCNI group, and this white is no thermodynamic data in the literature. So if you can see, there is so many white blocks. So before going to the successful operation of molten salt reactor, these blocks should be filled. So as a chemical aspect, there are lots of chemistry present in the molten salt reactor. As I say, molten salt reactor is a chemistry reactor. So determination of solubility product of the fission, solubility and fission product minor actinides, chlorine potential, corrosion study, thermophysical study, and the interaction between fuel and structural material, coolant and structural material should be there. I want to acknowledge Professor S. Kannan, Dr. S. Korida, Dr. S. Kelexip, and Sumanta Mukherjee for helping me this molten salt reactor slides, and Dr. Deepak Rawat, Pratik Das, Abhishek Rai, Hemlata Khadilkar, Vijmohan Singh, K.V. Modi, Sital Rao, all colleagues of my PhD and friends. Thank you.
Thank you. So, let's open for any questions and discussion, please. Because there are a lot of gaps to be filled up. I think they have only generated some permanent third order data.
Yes, sir.
So, if any questions,
moisture quantification, you have to do some Raman and all these things, or IR studies.
from the side of organizers, I have present duty to Thomas Samui with
এই